All right, so I'm going to talk about this technique of unfolding, which is a technique for evaluating Peterson inner products between some function f and an Eisenstein series zs chi, where the inner product is taken with respect to the z. That's why I write a dot. So here, f is going to be an automorphic function of weight 0 and character chi, in both of these level n. And recall that this, what I mean when I write this is the Peterson inner product. This is an integral over space upper half plane mod gamma naught n of f of z times e z s chi bar, and then the measure is dx dy over y squared. And when I write e z s chi, I'm thinking of the Eisenstein series ad infinity, and I'm going to use the series definition. So this is gamma in gamma naught n mod gamma infinity being the stabilizer of the cusp infinity. And here we had a gamma chi, or chi gamma bar times the imaginary part of gamma z to the s. So the way that we're going to do this is we're going to start by substituting this in to the definition of the inner product. So we get that the inner product is equal to upper half plane mod gamma naught n of f of z, and then here I'm going to write it like this: sum gamma in gamma infinity modding out gamma naught n of chi gamma bar, imaginary part of gamma z to the s, and then here I'm just going to write an asterisk here to indicate complex conjugation, because it's kind of unwieldy to put a bar over the whole thing, so this just means conjugation. And then we still have our usual measure. Next step is to swap the order of summation and integration. So this is equal to the sum gamma in gamma infinity modding out gamma naught n of chi, here we just have a chi gamma because it's a chi gamma bar, but we have a complex conjugate here. And we have our integral gamma naught n modding out the upper half plane. We have an f of z, and then the imaginary part of gamma z to the s with a complex conjugate, dx dy over y squared. And now in each part, make the change of variables. The change of variables is going to be z will map to gamma inverse z. So this is a different change of variables for each term in the sum. And what we end up getting is that this is a sum over gamma in gamma naught n mod gamma infinity of chi gamma, and then the domain we're integrating over is, well, going to be gamma inverse acting on this fundamental domain. And then we have an f of gamma. Maybe this should be, sorry, there should be no inverse here. Okay. And then we have f of gamma inverse z, and then the imaginary part of gamma times gamma inverse z. So this is just the imaginary part of z to the s. We still have our conjugate. And then the measure stays the same. And this is something that was talked about previously, that this measure is invariant under these Mobius transformations. Okay, and now this f of gamma inverse z, remember we are assuming that f is an automorphic function of character chi, so we get the sum still over the same gamma, and then we have our integral over gamma acting on this fundamental domain, so wherever it sends it. And then we're just going to use the automorphy here to write this as chi of gamma inverse times f of z. And then here I'm just going to write y to the s bar. So y is the imaginary part of z. And still the same measure. And then you see that this chi gamma and this chi gamma inverse cancel each other out. So we get the sum gamma in gamma naught n mod gamma infinity of this integral on wherever this sends the fundamental domain of f of z, and then here I'm going to write this as y to the s bar minus 1 dx dy over y for reasons that will become clear shortly. And now let's think about this sum and this integral. So we have, say, our fundamental domain. I'm just going to pretend that n is 1 to visualize this. So the fundamental domain looks something like this. This is h mod gamma naught 1. And then when we have these cosets, what we end up doing is we end up applying these transformations. Say there'll be one that takes the fundamental domain and flips it over, and then there'll be another one that maybe we'll translate it a little bit like this or something, etc. And all of these pieces end up being disjoint, and they end up essentially, or they end up tiling the strip between, well, here I've drawn it as between minus 1/2 and 1/2, but of course all of these things are periodic in X with period 1, so you can also think of it as the strip between X going from 0 to 1. So really, one shortcut is you can think of, there's cancellation, right, where you've got h mod gamma naught n, and then the gamma naught n mod gamma infinity, and the gamma naught n's kind of cancel each other out, sort of like fractions. And what you end up getting is an integral over, and it's the same integrand for each piece, so we can just consolidate them. And so you end up getting this integral over h mod gamma infinity. I recall that gamma infinity was the subgroup generated by the matrix 1, 1, 0, 1. So this is the stabilizer of infinity. And if you're doing things with SL2Z and not PSL2Z, then you want a plus minus here, because minus I also stabilizes infinity. And explicitly, this is the set plus minus in the matrices 1m01 for m ranging over the integers. So you get this quotient, and then you still have your same integrand. And what is this quotient? Well, essentially this is generated by the action of z mapping to z plus 1. So this quotient is going to be the strip y goes from 0 to infinity and x goes from 0 to 1 of f of x plus iy, y to the s bar minus 1 dx dy over y. Now how do we evaluate this? Well, let me maybe emphasize it a little bit more by writing the two integrals separately, like this. So this piece, this is really just picking off the 0th Fourier coefficient of our function f. To rewrite with more emphasis, this is the integral 0 to infinity, integral 0 to 1 of f of x plus iy dx y to the s bar minus 1 dy over y. Yeah, so this is exactly the 0th Fourier coefficient of f. And I'm going to call this f0 of y. So also, you can call this the constant term of f. So this ends up being equal to the integral 0 to infinity of f0 y, y to the s bar minus 1 dy over y. And this is the Mellin transform of the constant term of f, evaluated at s bar minus 1. By definition, right? This is the definition of the Mellin transform. Or you can view this maybe as the Mellin transform of the constant term divided by y, if you prefer. It's the same. So this is really useful, and the actual formula that we end up getting, that this is the Mellin transform of the constant term, that's something that I don't tend to use very much, but I instead just go through the technique of unfolding every single time I need it and compute the integrals as they come up, and don't really use this fact sort of on its own. The idea of the technique is more important, and the key step in the technique was to say, okay, we have an integral over h mod gamma naught n, and we've got our Eisenstein series, which is a sum of gamma naught n mod gamma infinity, and we're sort of canceling out this gamma naught n here and this gamma naught n here to end up with an integral that is going over h mod gamma infinity, right? So this sort of cancellation. And what we end up integrating over is, once we've written out the Eisenstein series, we get rid of the character and we get rid of this gamma.